This recording is going to cover the principles of gas exchange. Now, in an earlier recording, we discussed pulmonary ventilation, that process of getting air into and out of the lungs. But once we get to the air into the lungs, we want exchange of gases. We want oxygen to go from the alveoli into the blood and carbon dioxide to go from the blood to the alveoli. Now, at the level of tissues, we want the oxygen that's being delivered by the blood to go to the tissues in exchange for carbon dioxide. So we have to look at what some principles of gas exchange, things that would affect perhaps the rate of gas exchange. Now, one of the key things when we talk about just diffusion of gases is that the pressure of a gas will determine the rate in which it will diffuse from region to region. So we have to address these things about pressures. So the atmosphere that we breathe consists of a mixture of gases like oxygen and nitrogen, carbon dioxide, and other gases. Now that mixture that we breathe exerts a certain pressure that we refer to as your atmospheric pressure. Now, a partial pressure is the pressure of a single type of gas, and the partial pressure is directly related to the percentage of those molecules of that gas in that total mixture. And Dalton's law is actually a law that describes the behavior of non-reactive gases in that mixture, and it states that a specific gas type in a mixture exerts its own pressure. Thus, the total pressure created is, the total pressure exerted by the mixture gas is the sum of all the partial pressures of the gases in the mixture. So if we assume at sea level atmospheric pressure is 760 millimeters of mercury, we could calculate the partial pressure of each of the gases if we know the percentage of the gases that we're breathing. And actually, I'm going to show you real quick. So at atmospheric air, you'll notice that most of what we're breathing is nitrogen, and it's about 78.62%. If I actually did some math, and I did this times 760, I actually would get this number. If I did oxygen, you see here they give you 2. It's dependent upon if you round up or round down. So you can actually calculate the partial pressure of the gas at the atmospheric pressure is if you know that the percentage of that gas in the air. Now, if I come back here, I do want to show you though that what happens with atmospheric pressure is it will decrease as we go to higher altitudes. So at sea level, and Dallas is pretty close to sea level, the atmospheric pressure is 760 millimeters of mercury. But as we go to higher altitudes, that atmospheric pressure actually drops. So, but the thing is, the percentage of the air that you breathe up at, say, the summit of Mount Everest, it's still nearly 21% of the air that you breathe is oxygen. But if we did since I showed you kind of how we could calculate the partial pressure, it's still this percent, but it's percent of a smaller pressure here. So it would be that. So you'll notice the partial pressure of oxygen is much, much lower when we go to higher altitudes, which will play a role when we talk about gas exchange if we go to a higher pressure. Now, one thing though I do want to mention, since you see here the composition of air does change as it moves down through that tracheobronchial tree. So you see the partial pressures of, say, oxygen, carbon dioxide, and I would be familiar with these and the relative percent of those gases in the air that we breathe. You'll notice as in humidified air, so as air is moving through your tracheobronchial tree, it is becoming humidified. We're adding water vapor. The thing is, when we add water vapor, what we're doing is diluting out the other gases. The total pressure is still the same, but the partial pressures of the gases, you'll notice, are dropping. So you see oxygen is less. Now carbon dioxide, you say, well, it's still 0.3. If we move that out a few decimal places, it actually would be a little bit less. But it's such a small percentage, you don't see much of a change there. But you notice from here to here, water vapor pressure is increased. Now, once we get to the alveoli, you'll notice that the pressure's changed again. Again, focus on oxygen and carbon dioxide. So why is oxygen 104 millimeters of mercury? Why is carbon dioxide 40 millimeters of mercury? It all comes because what's happening? You have gas exchange. So if I kind of just draw a, here's an alveoli, and here's some blood vessel, is what's going on is oxygen is constantly being absorbed from the alveoli into the blood, and carbon dioxide is being excreted from and going from the blood to the alveoli. And so what you'll notice is oxygen's less from, say, if you compare it to humidified to alveolar air, because of the absorption that's taken place. CO2 is higher because of the CO2 going into the alveoli from the blood. These values, it's important to know, and they actually stay relatively constant, because despite maybe, say, changes in respiratory rate, as we do keep the levels of oxygen CO2 relatively constant. And so when you look at the partial pressures of these gases in alveolar air, they stay pretty close to what you see, the 104 millimeters of mercury for oxygen and 40 for carbon dioxide. Now, what I do want to talk about is some things that can influence the rate of gas exchange, and we've got to look at some different factors. So another law that we have to look at is Henry's law. This Henry's law shows us a relationship between partial pressure of a gas, the solubility of the gas, and how much of a gas that we can actually get into solution. Now, if you think about it, lining the alveoli, we have a layer of fluid that lines it. So how much of, say, oxygen am I going to be able to go from here, dissolve into that fluid? Eventually it's going to go across these tissues and into the blood, and then how much carbon dioxide can I get dissolved into that fluid? And actually, when you go over in this area, you're going to be, the plasma is fluid. So what is the relationship between that partial pressure of the gas and solubility and how much of that gas we can get into solution? So first thing, if you look at, it's actually the partial pressure of the gas. The greater the partial pressure of the gas, I'll be able to get more of that gas into solution. So I want you to think about when they carbonate soda. Now, what they're doing when they carbonate soda is they're going to use carbon dioxide, and they have a very high pressure that they're going to be able to force a lot of CO2 into solution, gives that bubblingness to the solution. So, and actually when you open up that bottle, though, the gas will come out of solution into the air. Now, the other thing that will influence the amount of gas in solution is how soluble that gas is. Now, if you compare the solubility of oxygen versus CO2, carbon dioxide is much more soluble than oxygen. It's about 20 times more soluble than oxygen. Nitrogen is it's very poorly soluble, but carbon dioxide is more soluble. So if I had the same partial pressure of oxygen and carbon dioxide, which is assume I had the same partial pressure, I would be able to get more carbon dioxide into solution than I would oxygen. Okay, so that's something just to keep in mind. Okay, so solubility of the gas will influence the concentration of that gas into solution, as well as the partial pressure of that gas. Now, another thing we need to look at is something called Fick's law of diffusion. This describes diffusion of gas through fluids. Now, I'm saying through fluids because gases are freely permeable in lipids, so that's not a problem. Getting through tissues is not a problem. Is what's going to dictate the rate of gas diffusion through fluids. And so you see an equation here, and don't freak out by seeing an equation, but think of it as a concept. So we're going to look at the different factors that can influence the rate of diffusion. Now, I'm going to not include the temperature because that should be relatively constant, so we're going to ignore that. So let's look at the different factors. So the big D represents the rate of gas diffusion. So the first thing is we call the solubility coefficient, which is this right here together. Now that is determined by the particular gas. So it's characteristics of the particular gas. If I compare the solubility coefficient of carbon dioxide versus oxygen, that's a much greater number for carbon dioxide. So if everything else was the same, and I'm saying if, you'd be able to get more carbon dioxide, or the rate of diffusion of carbon dioxide would be greater than oxygen. And I'm saying if, okay, so that's a big if. You can't really change that solubility coefficient of the gas, so that's kind of pretty much a constant. Now another thing that can influence it is your total cross-sectional area, the big A. Now notice it's on the numerator. So if I increase that value, so if I increase that, I would increase the rate of gas diffusion. If I decrease it, I would decrease the rate of gas diffusion. We're going to go through some scenarios in a little bit. The next thing that we look at is pressure differences. Pressure differences, I always say pressure differences always drive movement of stuff. And here we're talking about the pressure differences of the gases. So again, the delta P here is on the numerator, so it has a direct relationship with that and the rate of gas exchange. So if I increase the pressure difference, I'd increase that rate of gas exchange. If I decrease it, I decrease the rate of gas exchange. And again, we're going to give you some examples in a little bit. Now the last thing we look at is distance, which is expressed by the little d. Now that's on the denominator, so it has an indirect relationship with the rate of gas exchange. So in this scenario, if I increase distance, I'm going to have to, in other words, I have to travel a little bit further. That's going to decrease the rate of gas exchange. If I decrease distance, that would increase the rate of gas exchange. So those are various factors that can influence the rate of gas exchange. So we're going to do what ifs. What if I do this? How it's going to affect the rate of gas exchange. So first thing we'll look at, high altitudes. So you'll notice as we go to higher altitudes, starting from here, coming up, say the highest that we have is Mount Everest, is you notice that the pressure, the atmospheric pressure is decreasing. And as a result of that, that partial pressure of oxygen is decreasing. So if we look again at that equation, this, what we're going to be doing is we're going to be affecting this. So when you go to a higher altitude, the partial pressure of oxygen will decrease. So the pressure difference between what you have in the alveoli to what's in your blood is actually going to be decreased. So that will decrease the rate of gas exchange. And that's what can happen at higher altitudes. And that could lead to high altitude mountain sickness as a result of it. Also, another thing that could affect the rate of gas exchange is edema. And you have two different pictures here. There's edema that results in both of them. But think of edema as you've got an accumulation of fluid. And what that's going to happen is if you have an accumulation of fluid, the gases are going to have to travel a further distance to go through that fluid to where it needs to go. And so with this one, for that equation, what it's affecting is the distance, the little d. So here, distance increases, so the rate of gas exchange decreases. And again, this actually, pulmonary edema can be a result of a number of different things. Lack of surfactant, pneumonia, you can have it from going to higher altitudes too, and that is going to impair the rate of gas exchange. Now, atelectasis is a partial or a complete collapse of the lung. So you can have a loss of alveoli, but also You could have issues if I perhaps not necessarily have atelectasis, but if I block blood vessels. So I need to have matched ventilation with perfusion, the blood flow. So if I have issues with blood vessel flow or blood flow, or I collapse or destroy alveoli, that could affect the rate of gas exchange. So here you see a normal lung, you see the alveoli, and they're covered by all these little blood vessels. Now what happens with atelectasis? Well, you've got destruction here, and so that's going to impair the rate of gas exchange. And the reason why is the big A is affected. So we're going to have a decrease in surface area, and as a result, I'm going to decrease that rate of gas exchange. Now, another thing that could affect the rate of gas exchange, this time we're actually going to be a good one, is actually exercise. That would actually increase the rate of gas exchange. Thing is, how? Well, under normal circumstances, in normal upright lung, we actually have better blood flow down here than up here. Okay, down at the base of the lungs versus the apex of the lungs. Thing is, what happens during exercise as a result of pressures increasing somewhat, and with we call capillary recruitment. We're going to recruit blood vessels that were previously not opened. Is when you exercise, we call capillary recruitment. They become distended. That decreases resistance, which ultimately increases flow. And so what happens is during exercise, we're going to have more optimal, and all the way through the lungs, more optimal gas exchange because we're opening up previously unperfused blood vessels. And as a result, we're going to have an increased rate of gas exchange. So with this one, we're going to have an increase total cross-sectional area. So that actually increased the rate of gas exchange. Another thing, though, is we have an increase in delta P. So what actually happens is because you're exercising, your tissues are using more oxygen. When that blood makes its way up to the lungs, the partial pressure of oxygen is a little bit lower in that blood that's going to the lungs, and it's still that partial pressure of oxygen in the alveoli is 104 millimeters of mercury. Is the difference between that and the blood is going to be greater, so that helped to increase the rate of gas exchange. So exercise actually increases the rate of gas exchange, and think about it, that's what you want. So those are some things that can influence gas exchange. Now, one last thing I want to mention, and I've mentioned this in a previous recording, is external versus internal respiration. Now I'm going to change this because this drives me nuts when they're not correct. Is in the alveoli, the partial pressure of oxygen is 104 millimeters of mercury. Partial pressure of carbon dioxide is 40 millimeters of mercury. Now look at the blood that's coming up from the pulmonary arteries, going up into the alveoli, and you got those capillaries that are lining the alveoli, and the partial pressure of oxygen is 40 millimeters of mercury, and the partial pressure of carbon dioxide is 45. Now remember, gases want to go from high to low, and so oxygen is going to go from the alveoli into the blood, and by the time it leaves, that partial pressure of oxygen will be the same. I'm changing this to 104 millimeters of mercury. It'll equilibrate with what's in the alveoli. And if you notice the difference, it's about a 64 millimeters of mercury difference. So that's a pretty good rate of gas exchange there. Now, the difference between carbon dioxide, CO2, is greater in the blood than the alveoli. So you notice CO2 is going to go out. And the difference, though, is only 5 millimeters of mercury. That's not a problem. We can actually get away with a smaller difference in partial pressure with CO2 because carbon dioxide, remember, is 20 times more soluble. So we'll be able to get plenty of carbon dioxide out. And so again, though, as the blood leaves the alveoli, it's going to equilibrate with what you have in the alveoli, so it's 40, okay? So once we get down to the tissues, actually I do have to mention this. You notice down here, oxygen is 95, and we haven't had exchange yet. Now, the partial pressure of oxygen when it leaves the heart is actually going to be a little bit less than 104 millimeters of mercury. It's anywhere from 95 to 100 millimeters of mercury, and this is the reason why. Is the blood going to the left atrium, you got it from the pulmonary veins, plus you have blood coming from the bronchial circulation. Not a lot of it, but enough. And the bronchial circulation is part of your systemic circulation. And so that is going to be relatively deoxygenated. And so we get what we call a venous admixture. We have a mixing of blood from two venous systems. And so the partial pressure of oxygen that's going to leave the left side of the heart going out into the aorta is going to be a little bit less than you saw at the lungs. It's anywhere from 95 to 100 millimeters of mercury. When we get to the tissues, the oxygen is going to diffuse to the tissues because, again, you have a difference here. So oxygen is going to leave. Carbon dioxide is greater in the tissues because you're producing it from your metabolism. And the partial pressure of CO2 is going to cause that CO2 to go from the tissues into the blood. So up here at the level of the lungs, we see external respiration. At the level of the tissues, we see internal respiration. And a big thing that determines that rate of gas exchange is that delta P, that differences in pressure that determines the direction, definitely determines the direction. But other things that we'd mentioned before can influence the rate of gas exchange. Solubility of the gas, but again, we can't really change the solubility of the gas. You can affect it by distance and affecting the total cross-sectional area. So this is the last bit for the principles of gas exchange. Another recording is going to cover gas transport.